Analyze the continuous beam shown in figure by slope deflection method and draw bending moment diagram, shear force diagram and elastic curve. Here the beam is as shown in figure. In span AB it is subjected to 50 kN per meter and UDL over a length of 4 meter, and in span BC it is subjected to a point load of 120 kN at a distance of 2 meter from B and at a distance of 4 meter from C. Then in the end support end span CD, it is subjected to a point load at a distance of 2.5 meter from either C or D. First we have to calculate the fixed end moment. That is in span AB, that is M of AB. Here the fixed end moment is given by, that is minus, this one is subjected to UDL, that one is WL square by 12. Here the UDL intensity is 50, L is 4 square divided by 12. That one equals, if you calculate this, that one is 66.67 kilonewton meter. That one is anti-clockwise. Then at right side support, right end, that is B plus WL square by 12. Here that one equals again 50 into 4 square by 12, that one is 66.67 kilonewton meter. This one is clockwise. This is for span AB. Then M of BA. Now M of BC for second span, that is subjected to a point load. At B, that is anti-clockwise, WAB far end distance, that is B by L into L square. That one is, the load is minus 120 into A is 2 meter into B is 4 square divided by L is 2 plus 4, that is 6 square. That one is minus 106.67 kilonewton meter. Then M of CB, opposite end, that is at C, WAB by L, far end distance from C, far end is A, that is WA square B by L square. That one is 120 into 2 square into 4 divided by 6 square. That one is 53.33 kilonewton meter. This is the fixed end moment. Then M of CD, that one is subjected to a point load at the center at a distance of L by 2 from either end. That one is minus WL by 8 from C, that is minus, that is anti-clockwise, minus 80 into 5 divided by 8. That one is 50 kilonewton meter, that is negative. Then M of DC equals, that is clockwise, WL by 8, that one is plus 80 into 5 by 8, that one is plus 50 kilonewton meter. Here this is the first step. Then the second step is we have to write the slope deflection equation. Slope deflection equations. Here there are 3 spans. For each span you have to write 2 equations, one from left end and one for right end. Here, before going to write the slope deflection equation, the end condition, here we have to consider all the spans as fixed spans or fixed beams. AB is one span, BC is the second span, CD is the third span. By considering those, so you have to consider the separate spans and write the slope deflection equation. Here in span AB, theta A is 0 since that is fixed end. Before going to write, this one is theta A equals 0. Similarly, the last end, that is end support, that is fixed end, theta D is 0. Because they are the fixed ends. Here end A and end D are the fixed supports. Hence, the slope at the fixed ends is 0. That is at A and at D. Then here delta is equal to 0. There is no sinking of any support. You please write before going to write the equation. You know that the final moment or the slope deflection equation MAB equals, that is 2EI by length of AB inside the bracket, the near end 2 times, far end 1 times, minus 3 delta by L, plus, close the bracket, plus M of AB. That one is a fixed end moment. Here, by using this, by substituting the values here, if the flexural rigidity is not given, we have to assume that for AB, for BC and CD, there is no flexural rigidity. If it is constant, if there is any variation, we have to consider that. Otherwise, we have to assume that as uniform throughout the length of the B. Then this one is 2EI by length of AB, that is 4, 2 theta A is 0, plus theta B 1 times theta B, minus 3 into delta is 0 divided by 3 delta by L, then plus, close the bracket, plus, that is fixed end moment, that is minus 66.67. Then here you will get this one as 2EI by 4 into theta B. By simplification, this is 0.5 EI theta B, EI theta B minus 66.67. This one is MAB equals, you will get an equation in terms of unknowns and the flexural rigidity EI. This one is equation number 1. For E span, you will get two slope deflection equation, that is MBA. MBA equals 2EI by the length of AB is 4 meter. Then the near end, we are writing from the end B, near end is 2 theta B, far end is A, that is theta A, minus 3 delta by L, that is 4. Here theta B, theta A is 0, delta is 0, plus the fixed end moment, that is 66.67. Here after simplification you will get this one as 2 into 2 4, 4 by 4 1, EI theta B, expand this, then inside of the bracket the remaining things are 0, plus 66.67. This one is equation number 2. Here these are two equations for span AB. Similarly for interior span BC, that is MBC. Here MBC equals, the length is 6 meter, 2EI by L, that is 2EI by 6. Inside of the bracket, here the near end 2 times near end, that is B is the near end, 2 times theta B and 1 times theta C, minus 3 delta by L, that is length is 6 meter, here delta is 0, then plus, close the bracket, plus the fixed end moment for BC, that is minus 106.67. Here you will get 2 into 2 4, 4 by 6, that is 2 by 3, 2 by 3 EI theta B, plus 2 into 2 4, 4 by 6. Then here this one is 1/3 of EI theta C, then minus 106.67. Here this is equation number 3. Similarly for other end, that is CB, you will get, that is 2EI by L, that one is L is 6 meter. Inside of bracket, here we are writing from and C 2 times near end plus 1 times far end minus 3 delta by L, that is 6, then delta is 0 plus fixed end moment, that is 53.33 kilonewton meter. Then by this, that is, if we expand this 2 to the 4 by 6, that is 2/3 of EI theta C plus 2 by 6, that is 1/3 of EI theta C, EI theta B, delta is 0 plus 53.33. Here we have got one more equation for span BC. Then MCD, that is for last support, last span. Last span is, the length is 5 meter, 2 EI by 5. The length of CD is 5 meter. Inside of the bracket, the near end we are writing from C. Near end is C, 2 theta C. Far end is D minus 3 delta by L, that is L equals 5 meter, 2.5, 2.5. Here and D is fixed, hence the slope is 0. This term is 0. Delta is also 0. Then plus the fixed end moment here, that is anti-clockwise, that one is minus 50. Here this one equals, that is 2 into 2, 4 by 5 EI theta C minus 50. This one is equation number 5. Then MDC, that is 2EI by L, length of the DC is 5 meter. Inside of the bracket we are writing from end D, 2 theta, near end is D, 2 theta D plus far end is C, theta C minus 3 delta by L, that one is L is 5 meter. Theta D is 0 since that is fixed end, delta is 0, no sinking of the support, plus the fixed end moment, that one is plus 50, that is clockwise. Then here by this, by simplification, this one is 2 by 5 EI theta C plus 50. Here for there are three spans, you will get 6 equations. We have to write 6 equations. The third step is, after writing the slope deflection equation for each and every span, 2 equations for each span, now we can apply the equilibrium equations. By equilibrium conditions or equilibrium equations, equilibrium conditions, here that fixed end A and D, the moment is not equal to 0. The final moment at A and final moment at D is not equal to 0. If they are on simple support or roller support or hinged support, the end moment is 0. Here the end moment is not equal to 0. Then at intermediate support B and C, at intermediate supports B and at intermediate supports at B, summation of the moments of summation MB equals 0, that give us MBA plus MBC. There are 2 spans on either side of B. One is BA, one is BC. One is clockwise, one is anti-clockwise. Then by adding these 2 equals 0, that is, we will get the equation. If you simplify that, that one is 1.67 EI theta B. By adding the two things, that is 2 equations, then 0.33 EI theta C, that equals 40. Here theta B and theta C are unknowns. Then you will get 2 simultaneous equations. Then similarly at C, that is summation of MC equals 0. Here at C there are 2 spans, one is CB and another one is CD. One is CB and another one is CD. One is clockwise and another one is anti-clockwise. The summation of these two equals 0. After simplification, here 0.33 EI theta B plus 1.47 ei theta c that equals minus 3.33, that is equation number 2. Here you will get there are two unknowns and you will get two equations, two simultaneous equations. By solving these two equations, that is you have the calculator or by any method you have studied in mathematics, then how to get the solution for the simultaneous equation by solving equation 1 and 2. Here for theta a, theta b and theta c, theta b in terms of ei, that one equals 25.53 by ei. Similarly theta c equals minus 8.00 divided by ei. After getting the solution for the simultaneous equation theta b and theta c, now we can substitute these values of theta b and theta c. Substitute, that is for final moments. Now we want the final moments, that is to substitute the values of theta b and theta c in equations 1 to 6. In equations there are 6 equations, slope deflection equations. In equation 1 to 6, by substituting the value of theta b and theta c, then the final moments MEB equals, by substituting the value, that is I will substitute and I will give you the result, that is 53.9 kilonewton meter. This one is negative. Negative means that one is anti-clockwise. That one is 53.9 kilonewton meter. That one is anti-clockwise moment. Then MBA, here MBA, that one is, by substituting the values, that one is 92.20 kilonewton meter. If that is positive, that means that is clockwise moment. As per your sign convention of the moments, this one is clockwise moment. That one is clockwise moment. MBC, that one is, by substituting the values, you will get 92.20 kilonewton meter. This one is negative, that means that is anti-clockwise moment. That one is anti-clockwise moment. MCB, here by observing this MBA and MBC at joint B, it is in equilibrium. Summation of MB equals 0, that is MBA plus MBC equals 0. One is positive and one is negative. One is clockwise and another one is anti-clockwise. The summation of those two is 0. If there is a difference, if the difference is more, maybe in terms of fractions it is okay. If it is more than fraction, then you have to recheck or recalculate. Here at C, MCB equals 56.39 kilonewton meter, that is clockwise. Then MCD equals minus 56.39 kilonewton meter, that is anti-clockwise. Then MDC, here two for each span, MCB and MCD. Then at the end, that is end support, the support moment is MDC. That one is, by substituting the values, that one is 46.80 kilonewton meter. That one is clockwise, that is positive. Then here, once if you know the values of these moments, then you have to write here to draw the bending moment diagram. Here this one is your B. Here This one is subjected to UDL of 50 kilonewton per meter over a length of 4 meter. This one is A, this one is B. Then it is subjected to a point load of 120 kilonewton. This one is 2 meter, this one is 4 meter. This one is subjected to a point load of 80 kilonewton. This one is 2.5 meter, this one is also 2.5 meter, this one is C, this one is D. Now what we have got, the values of the moments, here we have to write. This one is MAB, that is negative, that is anti-clockwise. This one is anti-clockwise 53.9 kilonewton meter. This one is anti-clockwise. This one is clockwise. This one is anti-clockwise. Here both the values are equal. That is, there is a small difference, maybe a small difference, that is 92.20 kilonewton meter. Okay, you may consider any one value. Here MBA is clockwise, MBC is anti-clockwise. Similarly, MCB, that is 56.39, that is anti-clockwise, and then MCD is clockwise. This one is 56.39 kilonewton meter. Then this one is MDC, that one is clockwise, 46.80 kilonewton meter. If you draw this, then you can easily draw the bending moment diagram by extending these lines. Here draw a datum line or reference line. Here, by observing this moment, this one and this one in span AB, the support moments. These are the support moments what we have calculated. Here these support moments, both the moments are hogging. Here with respect to this reference line, one is 53.9, draw the ordinate of 53.9. Then similarly at the other end, that is draw an ordinate of 92.2. Here the variation is a straight line like this. Draw, join these two. Then from B to C, here the ordinate is 56.39. This moment is hogging, and I will show the with respect to the reference line. I will show it above the reference line or above the datum line. This one is, here I will write 53.90 kilonewton meter. This one is a hogging moment. This one is also hogging moment, 92.20 kilonewton meter. Here this one is 56.39 kilonewton meter. This is also hogging. In span CD, this one is hogging, this one is also hogging. Hence I have shown all the moments, support moments above the reference line or datum line, that is 46.80 kilonewton meter. This one is the support moment diagram. Then here it is subjected to, this one is negative moments. All these moments are negative moments or hogging moments. Here first we have to draw this support moments diagram. Over this we can overlap the span moment or be simply supported beam bending moment diagram. Here this one is subjected to, if you consider this one as a simply supported beam, then this is subjected to UDL of 50 kilonewton meter. The maximum bending moment is, that is parabolic like this. Here this one is parabolic, it is like this. Here the maximum ordinate is 50 WL square by 8. That one equals 100 kilonewton meter. This one is positive bending moment, this one is negative bending moment. This portion here, this is your net bending moment diagram. Only this shaded portion you have to consider. This one is the net bending moment. This white portion, that will cancel, both positive and negative moments get cancels. Here this one is subjected to, by considering this span BC, this is subjected to 120 kilonewton at a distance of 2 meter from one end and 4 meter from other end. Here the maximum ordinate is here, that one is a triangle like this. Below the point load, the bending moment is maximum. In simply supported beam subjected to UDL at the center, the bending moment is maximum. Here this moment is negative, that is support moment, and this one is positive. Below the point load, the bending moment is maximum. That is by overlapping these two bending moment diagrams. Here this one is 120 into 2 into 4, that is WAB by L. That one is 160 kilonewton meter. That one is maximum bending moment below the point load, exactly below the point load. Then in case of this one, this is subjected to point load at the center. Below the point load, the bending moment is maximum, that is it is subjected to a bending moment of, this one is only this portion, shaded portion, that is here this shaded portion is negative. All the support moments are negative moments, but this one is sagging bending moment, hence I have shown the positive sign. This one is negative. Then here the ordinate is WL by 4, that is 80 into 5 by 4, that one is 100 kilonewton meter. Here the shaded portion which give us, this one is shaded portion, that one is the net bending moment. Only this, that is shaded portion give us usually at the center of the support, at the center of the beam, the bending moment is maximum. At the central portion, that is sagging, and at the support section it is hogging. By observing this, here these are the maximum bending moments in span AB, BC and CD. Now we can calculate the